Okay, so welcome back, and now we're going to do a proof for case 1. Now to do the proof of case 2 from the previous video, it's just the contrapositive of what I'm going to do here. So I'm just going to do the proof for the first case. Okay, so let me read the first case to you so we understand. And again, you can follow in your notes. It says, suppose there exists an integer, capital N, such that 0 is less than or equal to a sub n, which is less than or equal to b sub n for all n greater than or equal to capital N. Then it says, if the series of b sub n converges, the infinite series of b sub n converges, then so does the series, the infinite series a sub n converge. Okay, so now, there's a couple assumptions here. One, we're assuming there exists an integer such that the nth terms have that relationship where a sub n is always less than or equal to b sub n, and they're positive. Okay? The second part is we're assuming the if part, right? We're going to assume that b sub n converges, and then we're going to use that information to conclude that the other series must converge. Okay? So the first thing we're going to do is start with our assumptions and then show that those assumptions lead to the conclusion that we are trying to prove. Okay, so let's start. So let's first let the sequence of partial sums, S sub k, be associated with the series of a sub n. Okay, so we're defining our series. Also, let L equal this infinite series from n equals 1 to infinity of b sub n, since b sub n is converging, right? So since b sub n is converging, we're going to say, we're going to let that real number, whatever that converges to, let's just make that equal to L. Okay, so now, where do we go from here? Well, since the terms are positive, right, of a sub n, so since all the terms are positive, so let's start with that. So since a sub n is greater than or equal to 0, so they're obviously non-negative, okay? Since this is true, then what does that give us? Well, what happens? Well, since all of the terms are non-negative, then this must be true. So if I take S sub k is equal to a1 plus a2 all the way up to a sub k, well then that's got to be less than or equal to what? Well, a1 plus a2 all the way up to a sub k plus a sub k plus 1. Okay? So why do we do that? Well, because we want to show that this is increasing, right? We want to show that this is an increasing sequence, right? And that does it. Since this is always non-negative, all the nth terms is non-negative, then the partial sum of S sub k is always going to be less than or equal to the partial sum of S sub k plus 1. Okay? Therefore, what? Therefore, the sequence of partial sums is increasing. Okay. Now, what can we say now? Well, let's take the other part. Well, we know since a sub n is less than or equal to b sub n for all n greater than or equal to some integer, positive integer, capital N, right? That's the assumption. Then what does that say? That means, since that's true, we know that the sequence for n equals 1, capital N. So beyond that, greater than or equal to. So for all n greater than or equal to n, so from capital N to infinity of a sub n, or no, we don't want to go to infinity, we just want to go to k, right? Of a sub n, that's going to be less than or equal to what? The same thing, n equals n to k of b sub n. But what do we know about b sub n? Well, that has to be less than or equal to the infinite series, right, of b sub n. And of course, that's equal to L. So now, because this is true, then we know this and this has to be true for all n greater than or equal to n. But then this is less than or equal to the infinite series, which is equal to L. So we know these two are less than L, right? Some real number L. Okay, now. So now, what do we know? Well, let's write it this way. So now, since this is true, we know that therefore, let's take the partial sum, s sub k, and let's just write it a little differently. Let's go from a1 plus a2 plus all the way to a sub capital N minus 1. Okay, so I'm just going to partition it this way. So I'm going to write this part, and then the other piece of it, I'm just going to write it as a finite sum. So this is going to be for n equals what? N, capital N to k, right? Why? Because I'm trying to get this piece in here, right? So this is going to be a sub n. Okay, so that's just our s sub k, right? So now what I'm doing is I'm taking this in here and I want to introduce and incorporate this fact here. Okay, now that's going to be less than what? Well, that's going to have to be less than or equal to what? Well, I'm going to now rewrite the partial sum, right? I'm going to rewrite this. So I'm going to take the first n minus 1 of these, so that's going to be less than or equal to what? a1 plus a2 plus all the way to a sub capital N minus 1. So I just repeated the first piece of this. Now, plus L. Right? Since this is true, right? Since this is true and this comes from that, since a sub n is less than or equal to b sub n for all n greater than or equal to some positive integer, capital N, then this relationship is true, must hold, right? Which means that therefore the partial sum from a1 through a sub capital N minus 1 plus the rest of the series, right, which is this, right? And now what I'm doing is I'm going back to this fact that S sub k is less than or equal to S sub k plus 1. Oh, and by the way, I missed a piece here. This is true for all, I missed one piece here. This should be for all, so let me do this. Therefore, for all k greater than or equal to 1, okay, this must hold, right? So basically I'm rewriting k plus x, or excuse me, s of x as this. But this is also less than this first, I'm just writing the first n minus 1 terms plus L, right? That's going to be true if this is true. So I know this sum is less than this sum, okay? Okay, so now, let me erase this because I'm running out of room on the bottom. Okay, now, since oops. Okay, so since that partial sum from a equals 1 to a, or excuse me, from a sub 1 to a sub n minus 1 is a finite number, we conclude that the sequence of partial sums is bounded from above, right? Because again, this is true for all k greater than or equal to 1. So this partial sum is always going to be less than or equal to this plus L. And so this is just giving us a finite number, right? We're just adding a finite number to another finite number. So for all partial sums, we're always going to have that partial sum that's going to be less than the same beginning part of the partial sum plus L. That's always going to be true. So therefore, the sequence of partial sums is going to be bounded from above. Okay, now, that pretty much gives it to us. Because what do we choose? We have an increasing sequence of partial sums, right? Now that we showed that it's bounded, well, the monotone convergence theorem. So therefore, by the monotone convergence theorem, the sequence of partial sums converges. And hence, the series from n equals 1 to infinity of a sub n also converges. Okay, or okay, and we're done. And remember, you could do the second case is just a contrapositive of the first case. Okay? Have a good day.